You ever just stop and think about the magic that's happening inside your phone or your computer? I mean, really think about it. It's this whole world, and it's built on a language that's so simple. It only has 2 letters, and today we are going to learn that language.
It sounds like a total paradox, right? How can a machine that basically just knows on and off create everything from a massive video game to a tiny little emoji? Well, the answer isn't some super complicated magic. It's actually a beautifully simple act of translation. And this is it. This is the whole secret. The secret handshake. Every single on state is just a 1, and every off state is a 0. That's it. Those 2 digits, 1 and 0, make up the entire alphabet for a computer. We call this system binary.
Okay, so here's the plan. First, we're going to start with those 2 simple letters. Then, we'll see how they build up to form numbers. After that, we'll get into the really cool stuff, how computers use them to, paint pictures and store just massive amounts of data. And to wrap it all up, we'll look at a clever little shorthand that coders use to speak this language way more easily.
All right, let's dive in. Section 1, the 2 letters. Look, before we can understand the language, we gotta understand the alphabet, right? And that means we need to go right down to the physical heart of the machine. So inside every single microchip, there are literally billions of microscopic switches. They're called transistors. And just like the light switch on your wall, they can only be on or they can be off. And because of that super simple physical limitation, everything a computer does has to be translated into a sequence of 1s and 0s.
And that creates this kind of translation challenge. We humans think in a base 10 system, which is called denary. The computer, it operates in a base 2 system, binary. And to bridge that gap, programmers often use a third system, hexadecimal, or base 16, as a much more human-friendly way to read those long strings of binary.
Okay, section 2, decoding the numbers. So how does this translation actually work? Let's take a look at how computers count by converting our numbers into their language. Well, the process is called conversion, and there are a few ways to do it. We're going to focus on a really straightforward and reliable method called successive division by 2. The logic here is actually pretty simple. You take your number, you divide it by 2, and you write down whatever the remainder is. Then you take the result of that division, and you do it again and again, all the way until you get to 0. The sequence of remainders you've written down, read backwards, is your binary number.
Let's actually see this in action. Take the number 165. You divide it by 2, you get 82 with a remainder of 1. Okay, now divide that 82 by 2, you get 41 with a remainder of 0. You just keep doing this over and over until you can't divide anymore. Then you read those remainders from the bottom all the way up to the top, and boom, there it is, 101000101. It's a simple mechanical process that works every single time.
Now, here's a great pro tip. For anyone studying this stuff, this is absolutely crucial. You have to understand the process, not just memorize the answer. Showing your work proves that you get the logic behind it, and honestly, that's what really matters.
Moving on to section 3, painting with bits. So representing numbers is one thing, right? But our digital world is full of text and images and sound. So how in the world do we paint that rich reality using only 1s and 0s?
Well, for text, it's all about agreement. We've created these standardized codebooks where every single character is assigned a unique binary number. An early version, called ASCII, was fine for English, but it really couldn't handle other languages. And that's why today we use Unicode. It uses more bits, which gives it enough unique codes for every character in every language, including, of course, everyone's favorite, emojis.
Sound is a little different. See, sound is a continuous wave, so we can't capture it perfectly. Instead, we take thousands of tiny snapshots of it every second. That's the sampling rate. Then, for each of those little snapshots, we describe its height using a binary number. And the more bits we use for that description, the more accurate it is. That's the sample resolution.
So here's the crucial point. This is the fundamental trade-off. A higher sampling rate and a higher resolution give you that crystal clear, high-fidelity audio, but the cost is a much larger file. It's a balancing act that's really at the heart of all digital media.
And that leads us right to our next big challenge. Once we've digitized everything, where do we put it all? And how do we make it manageable?
So how do we measure all this data? We're all used to hearing words like kilobyte and megabyte. But believe it or not, those terms are a little ambiguous. In computer science, we need to be precise. So the official standard actually uses terms like kilobyte and megabyte because they're based on the computer's native language of powers of 2. And this is the magic number. In the world of binary storage, everything is based on powers of 2. So a kilobyte isn't a neat and tidy 1,000 bytes. It's 2 to the power of 10, which is exactly 1,024 bytes.
And here's another one of those essential tips. Using 1,000 instead of 1024 is such a common mistake. In computer science, precision really matters. And that precision starts with using 1024 for all your conversions.
Now, to manage all this data, we use something called compression. Think of it in two ways. Over on the left, we have lossy compression. It's kind of like making orange juice from an orange. You get the essence, but you can't ever turn that juice back into the original orange. It smartly throws away data it thinks you won't miss. Then on the right, you have lossless compression. This is more like building a ship in a bottle. You can take it all apart and put it back together perfectly with absolutely nothing lost.
Okay, for our final section, let's circle all the way back to that third number system, hexadecimal. I know it might sound intimidating, but it's really the coder's secret weapon, and you interact with it every single day, whether you know it or not.
So why even bother with another system? Well, just look at a long string of ones and zeros. It's almost impossible for a human to read it without making a mistake. Hexadecimal takes those crazy long strings and represents them in a much more compact, manageable way. That's why it's used for things that need to be both precise and, occasionally read by a person, like your device's unique MAC address or the color codes on a website.
Here's a perfect example. On a website, this 6-digit hex code tells the browser exactly what shade of blue to display. The first 2 digits are for red, the next 2 for green, and that last pair, FF, turns the blue component all the way up. It's just a really elegant and efficient system. So, let's recap. Binary is for the machines. Hexadecimal is for the coders who talk to the machines. It all makes sense for now, but it leaves us with one pretty big question. As our technology gets smarter, and the conversations we have with our devices get way more complex, what's the next language we're all going to need to learn?